Hey guys, welcome back. In this video, we're going to be talking about drift speed. And by the end of this video, you will be able to determine the drift speed of an electron in a wire. So basically what you're able to do is figure out how fast an electron is going in a wire. So we know that in a conductor, electrons are moving around and that's what generates current. The question is, how quickly do those electrons actually move? In this video, you are going to figure out the answer to that question. So as in any experiment, it's also important to have some sort of theoretical model to explain what we see. So what I'm going to do is walk you through a theoretical model for current and drift speed. So we're going to go ahead and start with this cylindrical conductor, i.e. our wire. And the wire is going to have a cross-sectional area, which is going to be the area of the circular end of the wire. And we're going to call that A. We could find that by, for example, using the equation pi r squared and measuring the radius of the wire. So next, we're going to say that in this chunk of conductor, and we're going to go ahead and look at this blue chunk here, which still has that same cross-sectional area, we're going to say that it contains a bunch of electrons, so a bunch of charge carriers, that are going to have the charge Q. So we've got a bunch of little Qs, which I'll make yellow. So a bunch of little Qs in our wire. And we can also figure out the number of Qs. So we're going to say that each of these carriers is moving with a speed v. So they're moving at a speed v towards that positive terminal past point P. And we can also say that in the conductor, we're going to add a new quantity called N, which is the charge density. So that's the number of charges per meter cubed of conductor. So point P is going to have, so in 1 second, we'll say that NAVQ charges will pass through point P. So in other words, the charge density of our conductor times the cross-sectional area of the conductor times the speed of each individual electron times the charge on those electrons is equal to the charge going through point P in 1 second, or again, I. So I know that the drift speed of my electron is equal to I over N times A times Q. So this is a little bit of a confusing explanation, but I think it'll make a lot more sense once we work through an example. So in this example, we're going to have a copper wire of diameter 0.65 millimeters carrying a current of 0.25 amps. There are 8.5 times 10 to the 28th electrons in each cubic meter of copper, and the charge on each electron is 1.6 times 10 to the negative 19th coulombs. We are going to calculate the drift speed of the electrons. So let's go ahead and start with my givens. So I know that the diameter of my wire is 0.65 times 10 to the negative third meters, or 0.65 millimeters. We are going to be able to use this to find our area, but we don't currently know our cross-sectional area. We also know that the current in the wire is 0.25 amps. We know that there are 8.5 times 10 to the 28th electrons per cubic meter. So that means that N is 8.5 times 10 to the 28th. And that's going to be in electrons per cubic meter. And then we also know that Q is going to be the charge on each electron, which is 1.6 times 10 to the negative 19th coulombs. So our unknowns then are the cross-sectional area of the wire, which we can find using the diameter, and the drift speed of the electrons. So let's go ahead and write out our equations. So I'm going to go ahead and start out with the equation for cross-sectional area. So I know that A is equal to pi r squared, or pi times my diameter over 2 squared. So that's going to give me A is equal to pi times 0.65 times 10 to the negative third divided by 2. And we're going to square that whole thing. When I stick that in a calculator, what I'll get is that my area is 3.3 times 10 to the negative 7th square meters, which means that I am ready to use my drift speed equation. So for drift speed V, I can use the equation that I found on the previous, or that I found in the earlier explanation. So V is equal to I divided by N times A times Q, which means that I am ready to substitute and solve. So let's go ahead and plug in some numbers. So V is equal to 0.25, which is my current, divided by N, so 8.5 times 10 to the 28th, times A, which I just found as 3.3 times 10 to the negative 7th, times Q, which is 1.6 times 10 to the negative 19th. Oh, just barely fit in there. So when I stick that all in a calculator, what I'll find is that the drift speed of my electrons in my wire is 0.055 millimeters per second. So what I'll do is I'll find it in meters per second, multiply by 1,000, and that's going to give me the millimeters per second. So let's start with a thought experiment. So we just found in that question, in the earlier problem, that the drift speed of the electrons is very slow. It's less than a millimeter per second. So if electrons are moving so slowly, why doesn't it take longer for a light to turn on when you flick the light switch? So what I want you to do is take a moment and think about it, pause the video, and come up with your own theory. So hopefully you have paused the video and have a theory of your own for why the drift speed of electrons, or why lights don't take forever to switch on. So the reason for that is actually a lot simpler than you might think. So let's take a look at our circuit. I'm going to go ahead and just draw a very simple circuit with a battery and a light bulb. And I'm going to go ahead and draw the wire. And I'm going to go ahead and draw in the wire all of the electrons. So I've got a bunch of electrons in the wire. And the thing is that I have electrons throughout the wire. So for my light bulb to turn on, I don't have to wait for an electron at the negative terminal to get all the way through to my electron, or to my light bulb. I just need to wait for the electrons near my light bulb to start moving. And as it so happens, the signal that electrons should need to start moving is going to travel through the circuit much more quickly than the electrons themselves. So all the electrons in the circuit will start moving almost instantaneously once you flick the light switch on. And so rather than having to wait for this electron over here to get to my light bulb to get started, the light bulb just really needs to wait for the electrons right next to it to start moving through it. So what that means is that while electrons are moving slowly, lights and other parts of electric circuits can light up almost instantaneously. So let's talk about takeaways. First of all, the drift speed of an electron is dependent on the area of the wire, the current in the wire, and the charge density of the wire. It's also dependent on the charge of the electron, but since that's constant, I am not going to add that in here. Finally, the drift speed of the electron does not affect how quickly components in a circuit turn on. So components in a circuit will immediately turn on when you flick a switch because all of the electrons of the circuit will start moving almost instantaneously.